centuries, a narrow strip of water stood between Britain and the rest of Europe, shaping history, politics, and identity. Above it, one of the world's busiest shipping routes never slept, crowded with thousands of vessels every year. Below it, cold, shifting waters pressed down on a seabed known for defeating human ambition. The channel was more than a crossing. It was a psychological barrier widely believed to be untouchable. For over 200 years, the thought of passing beneath it seemed unrealistic. Even so, the idea refused to fade. As early as 1802, engineers were already imagining a tunnel beneath the English Channel. At the time, the plans were almost absurd by modern standards. Horse-drawn carts, oil lamps, manual excavation. The technology simply did not exist. Still, the dream persisted. In the late 1800s, workers even began digging early test tunnels from both sides. Water intrusion, political fear, and military concerns shut the projects down. Britain, in particular, feared invasion through a tunnel. The sea remained undefeated. For nearly 2 centuries, the project failed before it even began. Everything changed in the second half of the 20th century. Advances in engineering, geology, and tunneling technology finally made the impossible seem achievable. In 1986, Britain and France signed a historic agreement that officially approved the construction of a fixed rail link beneath the channel. This time, there was no turning back. What makes this project even more remarkable is how it was funded. No direct government money, no safety net. The entire tunnel was financed privately by investors who were betting billions on an idea that had already failed multiple times in history. If the tunnel failed again, the money was gone. This was not just a tunnel, it was a gamble on human precision. The design itself was ambitious. Instead of 1 tunnel, engineers planned 3. 2 large rail tunnels running side by side, carrying high-speed passenger trains, freight trains, and vehicle shuttles. Between them, a smaller service tunnel. That central tunnel would be the heart of the system, used for maintenance, ventilation, and emergency evacuations. Construction began in 1988. On the English side, crews carved deep into the iconic White Cliffs near Dover. Over 250,000 cubic meters of chalk were blasted away just to create a flat working platform. The excavated material was not discarded. It was dumped offshore, slowly forming an entirely new stretch of coastline. Britain literally reshaped its land to make the tunnel possible. On the French side, engineers dug a massive circular shaft over 60 meters deep near the coast. This shaft allowed tunnel boring machines to be lowered underground and launched directly into the rock. Once these machines started moving, stopping them was extremely difficult. Every decision had to be right. The greatest challenge was invisible: geology. Beneath the channel lies a narrow layer of rock called chalk marl. It is strong, stable, and mostly watertight, perfect for tunneling. The problem was its thickness. The safe layer was only about 20 meters thick and sat roughly 75 meters beneath the seabed. Drift slightly upward and the machines would hit porous rock, allowing water to rush in. Drift too low and dense clay could jam or crush the machinery. Engineers spent years mapping the seabed using seismic surveys and drilling samples before committing to a route. Once tunneling began, there was no room for error. To excavate the tunnels, 11 massive tunnel boring machines were custom built. These were not off-the-shelf machines. Each one was a moving underground factory. The cutter heads alone weighed hundreds of tons and were designed to grind relentlessly through solid chalk. As the machines advanced, they installed pre-cast concrete segments behind them, sealing the tunnel almost immediately. Those concrete rings were the only thing separating workers from millions of tons of seawater above. Conditions underground were extreme. Temperatures rose to dangerous levels. Ventilation was limited at the excavation fronts. In some areas, workers labored in pressurized environments to prevent water ingress. On the French side, looser and wetter ground required sealed machines operating under constant pressure, turning parts of the tunnel into underground pressure chambers. Every meter forward was a risk. Water seepage was constant. Even a small leak could escalate into a flood. Crews monitored the tunnel walls continuously. Any sign of moisture had to be sealed immediately. Entire teams were on standby, ready to inject grout into the rock at a moment's notice. Precision was everything. The tunnels were being excavated from both sides simultaneously, drilling blindly toward a single meeting point beneath the sea. Engineers relied on gyroscopes, laser guidance, and advanced surveying systems to maintain direction. The machines were steered almost like vehicles, with constant micro-adjustments to stay within the thin chalk layer. At the same time, logistics above ground were staggering. Over 7 million cubic meters of excavated rock had to be removed and processed. On the British side, this material created nearly 90 acres of new land. On the French side, spoil was transported inland. Coordinating this flow of material while running dozens of machines underground was an engineering operation on its own. The service tunnel was excavated first, acting as a test path. Once its success was confirmed, the larger rail tunnels followed. These tunnels had stricter requirements. They needed to support high-speed trains, electrical systems, pressure changes, and emergency access. The tolerances were measured in millimeters. After nearly 40 kilometers of tunneling, the moment of truth arrived. In December 1990, the two excavation fronts were separated by just a few meters of rock. One final pilot hole was drilled. When the barrier broke, workers from Britain and France met face-to-face beneath the sea for the first time. The alignment error was less than half a meter horizontally and vertically. After drilling nearly 40 kilometers underground, that level of precision was almost unimaginable. The tunnel boring machines met different fates. On the British side, the machines were too large to dismantle efficiently. Instead of wasting months, engineers sealed them in place permanently. 6 enormous machines were buried beneath the channel forever. On the French side, the machines were dismantled and brought back to the surface. Excavation was only half the battle. The tunnel needed air, power, light, and safety systems. Massive ventilation fans were installed to constantly circulate fresh air. Electrical infrastructure was added to power trains using extremely high voltage. Tracks were precision welded to handle speed, heat, and vibration. Fire was the greatest fear. Trains moving underground push a powerful wall of air ahead of them. A fire could spread rapidly if not controlled. To counter this, emergency cross passages connect the rail tunnels to the service tunnel every few hundred meters. Fire suppression systems line the entire length of the tunnel. The tunnel officially opened in 1994. The engineering achievement was undeniable. Financially, the project struggled. Costs had nearly doubled from early estimates, reaching the equivalent of over $15 billion. Investors faced years of restructuring, but the tunnel worked. Soon after opening, the ultimate test arrived. A fire broke out inside a truck shuttle deep underground. The safety systems activated exactly as designed. Passengers evacuated through the service tunnel. Every life was saved. Today, trains cross beneath the English Channel at speeds of up to 160 kilometers per hour. Travel time between London and Paris is just over 2 hours. No airports, no security lines, a seamless journey beneath the sea. What was once considered impossible is now routine. A permanent link of steel, concrete, and human precision. One of the greatest collaborative engineering achievements in history. Thanks for watching.